This is the second of two videos on ellipses, parabolas, and hyperbolas, which arise by intersecting a cone with a plane. In the first video, we saw how to write down equations of conic sections, how much freedom we have in moving conic sections around, and how that affects the equation, and how we can leverage that freedom to write the general equation of a conic section in one of the two standard forms, which we're looking at there at the top of the page. So let's pick up where we left off. Let's see here. We can simplify even more by rescaling, if we'd like. So let's just see here an example. Let's suppose we have this equation of an ellipse here. X squared plus 36y squared is 9. Rewrite it like this, dividing everything by 9, and we can rewrite it like this, just a little bit simpler. And if we wanted to graph this, we might do it by looking at, say, the x and y intercepts. So if you set y equals 0, you'll get x-intercepts of plus or minus 3. And if you set x equal to 0, you'll get y-intercepts of plus or minus a half. So you'd have this ellipse like this in red here. Now suppose that you wanted to just maybe measure things a little differently. So I'll write here that that's the point where x is 3 and that's the point where y is a half. But suppose you wanted to measure things just in slightly different units, where you actually want to view 3 as representing 1 unit. So you might introduce new letters u and v, where u is x over 3 and v is 2y. And then this equation would just become u squared plus v squared equals 1. And if you were to graph that on axes where u and v are, have sort of equal spacing, then you would get the unit circle. So by rescaling, rescaling the coordinate axes, you can sort of shrink or expand the curves. So in a basic sense, it's enough to study these curves, ellipses, parabolas, hyperbolas, in these standard forms where a and b are either plus or minus 1. And then we can get all the other shapes by rescaling, translating, rotating. So here are the possible cases. A and b are plus or minus 1. Let's just write them down. Y equals x squared, y equals minus x squared. X squared plus y squared equals 1. Circle. X squared minus y squared equals 1. There's a hyperbola like that. And minus x squared plus y squared equals 1 is a hyperbola like that. Finally, you could take minus x squared minus y squared equals 1, but that has no real solutions. Now, these first two can be grouped. Unit circle is the unit circle, and those next two can be grouped. The two parabolas are just flipped, and the two hyperbolas are just rotated 90 degrees. So you really have three basic curves that you'd like to study. These are the really, really basic conic sections. So, if we can boil things down that much by just choosing coordinates to describe things really, really simply, why would we study any other equations of conic sections? Why don't we just wipe out every other quadratic from the textbooks and just look at equations like this where the coefficients are 1? While it's true that if you were just, say you came home and you saw a parabola or an ellipse or a hyperbola drawn on your desk and you wanted to just study that curve, you could choose coordinates to describe that curve in a really, really simple way. That's true. But if we choose coordinates to describe a curve in a really, really simple way, the other objects around that curve may become more complicated to explain. So typically we don't study just things just on their own. We might study how they relate to other shapes nearby or that sort of thing. So if you had, for example, two parabolas, so there's one, you choose coordinates, there's another, you choose coordinates, but the coordinates you choose to make one simple might make the other complicated. How would you know which to choose? So that's just kind of a basic thing in mathematics and problem solving in general. How do you describe aspects of the problem so that the problem as a whole becomes most elegant and easiest for us to solve? If you make one part of the problem if you describe one part of the problem really simply, another part of the problem might become more complicated. That's just kind of general stuff. So after boiling things down to conic sections that are this basic, we need to be able to recover some of those degrees of freedom in order to actually apply this stuff, in the real world, so to speak. So how do we recover those degrees of freedom? This is maybe familiar. So we can translate by replacing, for example, x by x minus a, or y by y minus b. So for instance, if you have a unit circle here, centered at the origin, if you shift x and y, you can get a circle centered at the point AB here. So and this equation would look like this. Or so that's translation. Or you could rescale. So you could replace maybe x by a times x, or replace y by b times y. So you could expand or shrink the coordinate axes, or equivalently, expand or shrink the curves in the coordinate axes. So there's y equals x squared, and there's y equals 4x squared, or 2x all squared. And what about rotation? Well, rotation is just a little bit trickier. Translation and scaling we typically see in high school. Rotation is a little trickier. And let me just give you an example of it here. Let's look at a hyperbola. If you look at the hyperbola x squared minus y squared equals 1, let's just factor it, just for fun. Factor the left-hand side. You can write it as x minus y times x plus y equals 1. Now there's the curve of it in the xy plane. Now let's just give x minus y a new name, u, and let's give x plus y a new name, v. Then the equation becomes uv equals 1, and if we were to graph that in a uv plane, the curve would look like this. So with u equals x minus y and v equals x plus y, we get a different curve in the UV plane. Now, you could write this using matrix algebra. Now, if this isn't familiar, that's okay. It's a nice precursor of how useful linear algebra can be. This matrix here is like a rotation matrix and also a bit of a dilation by root 2. So we can rotate curves in this way as well, but it's just a little bit more advanced. It helps to have some linear algebra, some linear transformation theory under your belt. Just for fun, let's see what happens to this basic parabola in these new variables, u equals x minus y and v equals x plus y. You can work this out. You would get a description in terms of u of v that looks like this. This is an implicit equation, and the curve looks like this. And maybe one reason why we don't bother so much with rotation in high school is because if you rotate these curves around, suddenly you get things that don't pass the so-called vertical line test, and so they aren't functions properly defined, that sort of thing. But they're still curves. They're still curves. They're still worthy of study. Now finally, let's just consider this basic equation of a conic section in the xy plane, a, b, c, d, e, and f. Is there a way, a simple way, to determine whether an equation like this describes an ellipse, a parabola, or a hyperbola? It turns out there is. The quantity b squared minus 4ac. Let's write that down. Now, b squared minus 4ac. You take that, you compute it, and if it's less than 0, it's an ellipse. If it's equal to 0, it's a parabola. And if it's greater than 0, it's a hyperbola. Fascinating. Now the value of b squared minus 4ac may change when we change coordinates, either rotating or translating. But its sign won't change, no matter how you change the coordinates. Now, finally, let's just notice this, that the fact that b squared minus 4ac negative gives an ellipse, well, there's some wiggle room there. There are all sorts of negative numbers. Similarly, if b squared minus 4ac is positive, you get a hyperbola. There are all sorts of positive numbers, so there's some wiggle room there. But only if b squared minus 4ac is 0 do you get a parabola, and there's no wiggle room there. 0 is 0. So this has been a little introduction to conic sections and how you might manipulate them and boil them down to basic forms and then recover some of that freedom. So I will likely follow this up with a video on quadric surfaces in three-dimensional space. Thanks for watching.